Let us now complete this brief survey of history of cosmology with some more modern developments. Remember that by 1970s it became clear that galaxy formation evolution must play an important role and must be understood before we can actually map out the universe. And both theoretical and observational advances were made. Three theorists deserve special mention: Jim Peebles in United States, Yakov Zildovich in former Soviet Union, and Martin Rees in United Kingdom. At the same time, we saw development of numerical cosmology. It is impossible to analytically follow how would systems of billions and larger numbers of particles evolve, but we can simulate them in a computer. The improvements in computer technology enabled very sophisticated and ever better simulations to be done, and here is just a set of snapshots from one by a theorist named Andrei Kravtsov. Today, this is a very well-developed art, and this is just a small snapshot of one of the more modern simulations by so-called Virgo Consortium, and it covers essentially the entire observable universe. We can also zoom in great detail and see how structures form on galactic scales. So then that has to be compared with observations. Observational cosmology really started blossoming from 1970s onward, and thanks largely to the development of many new technologies, and both from the ground and space. This is a picture from Hubble Space Telescope, one of the deep fields that Hubble has studied with many, many distant galaxies. But it's important to point out the important role that technology plays in our development of scientific knowledge. Ever better instruments, including CCD arrays and computers, enable us to get much higher quality of data and much more data than we ever had before. And then both large telescopes on the ground, like a twin Keck telescope shown here, and in space, like the Hubble shown here, also play an important role in these studies. Another important theoretical development happened in 1980. Alan Guth came up with so-called inflationary theory. And this was a very surprising thing, and it really addressed a number of important questions in cosmology. It became a standard paradigm in which early universe is viewed. We'll talk about this in much more detail later. Other theorists since kept developing better or more ornate versions of inflationary theory, one of which is the multiverse or megaverse, in which ours is just one of the many inflating bubbles in some much larger space. But so far, that's entirely a hypothetical issue. 1990s, mid-1990s, really saw a return to the classical cosmology of cosmological tests. Now we talk about precision cosmology. Two important paths happened there. The first one was studies of a cosmic microwave background with exquisite precision, both from ground, from balloon-borne instruments, and from space. And cosmic microwave background is not perfectly uniform. There are some minor fluctuations, like parts in million, that correspond to density fluctuations in the early universe. Measuring their size can constrain cosmological parameters. So this is now done with great precision. But second thing that happened was use of supernova explosions as standard candles with more modern instruments to push Hubble diagrams much deeper than was done before. And turn out that that can also constrain cosmological parameters in important ways, and it became one of the key ingredients in the discovery of dark energy. So this is just to illustrate the great precision by which we know cosmological parameters. You can look through them, and there are many different ones, but they're roughly known with percent level precision. This is something that earlier cosmologists could only dream about. So cosmology is now a precision science, and we know properties of the universe with an amazing accuracy. Just to jump ahead, here is the punchline, that today we know that the universe consists about 73% of so-called dark energy, another 23% or so of dark matter, which is not made out of regular matter atoms, and normal matter that we know about constitutes only 4%. This is now determined through many, many different observations using different methods, and it's supported constantly and refined with new measurements. And it's generally a well accepted picture, and we'll talk how that's done in more detail later. So here is essentially a cosmic timeline from the modern viewpoint. Universe starts with Big Bang. There is a brief period of inflation when the universe is less than 10 to the minus 32 seconds old. Then sometime later, physics that we know starts to come into play, such as formation of first chemical elements, and then slowly formation of large fluctuations, and the formation of galaxies and their evolution. Obviously, the deeper in the past we push in this logarithmic scale, less we understand. But it's actually impressive that we can really address what happened in the universe when we say nanoseconds old with reasonably good accuracy. Here is a slightly different view that would be appealing more to physicists, that expresses history not as a function of time, but as a typical energies of particles at that time. Recall that the smaller and the denser the universe was, hotter it was, and kinetic energies were higher. Well, today, they're roughly micro background photons, which is energies of 1/4000th of an electron volt. At earlier times, the energies were correspondingly larger, and inflation happened when particles had energies of 10 to the 16 giga-electron volt. Just for comparison, the Large Hadron Collider produces particles of about 100 giga-electron volt rest mass energy. Here we see a simulation of what early universe might have looked like that was produced by the WMAP space mission team, and shows fluctuations in microwave background that was studied with great precision. Zooming in on one of them, you can see schematically dark matter collapsing, making clumps, then stars igniting, first chemical elements are made, galaxies are slowly assembled. Another interesting way to visualize the history of the universe is to say if all of the age of the universe, 13.7 billion years today, was squeezed in one day, what happened when? Well, Big Bang happens at the beginning. Pretty much everything that predates formation of our solar system is done in first few hours. On that time scale, humans appear 4 seconds before midnight, 4 seconds out of entire 24-hour day. And that gives you a little bit of a scale as to how significant our history is on cosmic scales. Martin Rees suggested that cosmology today is now developing in two directions, one of which he compared to chess, which is theoretical, elegant cosmology, which is very precise and clean, and the other one, which is observations of galaxy formation, which is messy, and he compares it to the mud wrestling. Both of them are important and interesting.